unit 2. Okay, so in this unit 2, we have centrifugal compressors and axial flow compressors. So let's start with the centrifugal compressor. So what I'm showing is a schematic of a centrifugal compressor. Schematic or the construction of a centrifugal compressor. If you look at it, so see it has an impeller. See what it is. What I'm showing you. This has an impeller. Okay, it has an impeller. Then it has a casing. See, you call it as a diffuse. No, this is the casing actually. This is the casing. So what I'm showing is a cut section of it. Okay. Then I do have. See, there are certain blades you can see. These are called as the fixed blades or diffuser blades. Okay, and this will ensure the fluid is accelerated, that is it gets converted from, see I am going to get converting the kinetic energy to your pressure head actually. That what happens in a part of your diffuser plates or diffuser thing. Then whatever I am going to see this diffuser or the casing. So this casing also will head it. So a part of the energy is converted from kinetic energy to the pressure energy in the diffuser plates, or we call it as outer static plates or static blades, and a part is converted in your diffuser casing, or you call it as a casing or whatever it may be. Now the fluid will be entering in this fashion. That is, it is called as eye of the impeller. So this is the eye of the impeller. See, the fluid enters at the eye of the impeller and it goes exactly radially. If you, for example, if this is my axis, this is the axis, so exactly perpendicular. So this is the radial direction. So that's why all the centrifugal, maybe whether it is a pump or a compressor or whatever it may be, so they are called as centrifugal as well as radial flow machines. Why? Because the flow is exactly the radial direction. So this is a simple construction of your centrifugal compressor. If I am using a water as a fluid, then it becomes centrifugal. So there won't be any much difference between it actually. Maybe the size matters. So the size of the compressor for the same quantity of the fluid, the size of the pump for the same quantity of fluid, it matters because of the density or the type of medium I'm trying to handle. Okay. Now I'm showing you the blown up view of it actually. So what you see on the right hand side is a fixed vanes or guide vanes, what we call this one. So the fixed vanes are, see this one, diffuser plates or whatever I'm going to call, no. So that means, see the fluid will go here, see the fluid will, this is the inlet, okay, fluid will go in and from the impeller it will come out like this, it will come out. Then whatever that comes out from the fluid, from the impeller, it goes to this particular guide vanes and then it come out. And then it goes through your casing, then it comes out of your whatever we call it as an output or your delivery pipe or whatever it may be. So in your construction wise, what are the parts of a centrifugal compressor? So it has an impeller, and if you closely look at the blades, all the blades are twisted. They are twisted actually, and they are twisted in such a way that flow enters. See, it's always parallel. See, the flow is almost at the inlet is axial, but at the exit. So, with respect to the flow at the radial, maybe exit direction, we call this machine a radial flow machine or centrifugal. So, because of the centrifugal action, the fluid is thrown out actually. So, once it comes out, it will be having very high kinetic energy. Okay, I'll be having a very high kinetic energy. That kinetic energy, part of the kinetic energy is converted in your guide vanes or fixed vanes, and part is converted in your what we call it as a casing. So that at the exit, I'll be having the pressure energy or pressure head. I'll be having a pressure energy or pressure head. So I need to deliver the fluid to a particular height. Okay, so maybe 3 meters, 5 meters, 10 meters, that's how we're going to define it. So if I'm trying to handle a compressible fluid, so it is called as a compressor. If I'm trying to handle a incompressible fluid, it becomes a pump. Okay. So before I proceed and do a derivation for the expression for the pressure ratio, Let's look at a simple classification. I'm going to simple classification of these compressors. So that's very much required. Now, see, when I speak of a compressor or when I speak of this particular fluid, so depending upon the type of fluid I'm trying to handle. Okay, if I handle compressible fluid, if I try to handle compressible fluids, so I may end up with some kind of a devices called as fans, blower, and compressor. Okay. If I try to handle the incompressible fluids, so I may end up with pumps such as the working fluid will be either water or oil or whatever it may be. So this is a major simple classification: compressible fluids on one side and incompressible fluids on the other side. So under compressible fluids, so under one, so depending upon the pressure ratio, see, under one, so I have the fan. Okay. So the fan, if my pressure ratio, what is this pressure ratio? It is a ratio of the fluid at the outlet to ratio of the fluid at the inlet. Okay, that is the pressure. So pressure at the outlet to pressure at the inlet. So if the pressure ratio is very small, so if the pressure ratio is somewhere between 1.02 to 1.07, that is exit pressure to inlet pressure. If the ratio, if I take actually, if the ratio, that means I am trying to have a small increase in the pressure. For such things, if the pressure ratio is very small, I'll get a device what is called as a fan. Okay, this is 1A. Now 1B, so we have the next one is blower. If my pressure ratio is slightly higher than the fan, okay, that is around 1.1 to roughly around 2, then I call that as blower. So here in blower, I'm trying to handle a little bit slightly a larger quantity of the fluid at a little bit slightly higher pressure. Now, anything above 2, if the pressure ratio is anything above 2, I will end up with what is called as, if the pressure ratio is greater than, that is more than 2, I call such machines as compressors. Even in compressor, I will go for, see, in this actually I will go for a single stage and multi-stage. Single stage and multi-stage. What is single stage? Suppose if my pressure ratio is, okay, if I call that as PR, it is greater than 2 and less than 10. Okay, if the pressure ratio is between 2 and 10, I will end up with a single stage compressors. If I want a pressure ratio more than, if the pressure ratio is more than 10, I will go for multi-stage compressions. A single stage I prefer till the pressure ratio is around 10. Then if the pressure ratio is more than 10, I will go for a multi-stage compression. Even in this case of single stage or multi-stage compression, so we do have a further classification. So those are called as radial flow compressor or centrifugal compressor. Here also I will have single stage and multi-stage. So here, what will happen in case of a radial flow? The flow is in radial direction. The flow is in radial direction. So here I have the second classification. So that is your axial flow compressor. So here, the flow is in axial direction. So that's the major difference. The flow is in radial, that is exit flow. I'm looking at the flow or the exit is in radial direction. I call it a centrifugal compressor or radial flow compressor. If the flow or the exit is in axial direction, I call that as axial flow compressor. And also one more thing we have to note here. So whenever I want to handle more mass flow rate, see whenever I want to have more mass flow rate, I will go to axial flow compressor, and the radial flow for the same pressure ratio. Say if the pressure ratio is 10, if the pressure ratio is 15, if the pressure ratio is 20, I want to handle more mass flow rate, preferably I'll go for axial flow compressor. If I want the same pressure ratio, at the same pressure ratio, slightly lesser mass flow rate, I will go for centrifugal compressor. So now, depending upon the quantity of the fluid I'm going to add, I will choose the what type of compressor I'm going to use. Now, even in multi-stage compression, we have arrangement in maybe what we call it as parallel connection and series connection. So if I want more discharge, I'll go for parallel arrangement. If I want less discharge, I'll go for series arrangement. Let me simply construct and show that. So if I want parallel, so if I want a parallel connection, so parallel multi-staging, what is it? Parallel multi-staging means, so I'm going to have, so for example, I will have a compressor number 1, I will have a compressor number 2, I will have a compressor number 3. So all are of same thing. So what is the input actually? Say it will be P1, this is P1, this is the P1. So P1 is atmospheric, it's coming out. So now what is the pressure is going to do? It is, I am compressing it to a pressure P2. So all are at the same pressure ratio. But it comes out, what is the discharge that is coming out? Either it can be a mass flow rate or discharge, depending upon whether I'm going with a compressible fluid or even incompressible fluid. So it comes out with Qm dot 2 or Q2, m dot 3 or Q3, whatever it may be. Now, say I want to connect all those things. Say I want to connect all to the single manifold. So what will happen? Say if from one I'm getting Q1, from second compressor I'm going to get Q2, from third compressor I'm going to get Q3. So it's a single manifold. Okay. Now when I'm going to go for a parallel thing, that means for the same exit pressure and high discharge, I want same exit pressure at high discharge, I will go for parallel connection. So when I can go for a series connection, series multi-staging. So when I can go for it actually, what are you going to do actually? So this is my compressor 1, okay, I have an input P1, okay, so let the output from it is Q1. So this becomes an input to the next compressor. So I have a second compressor here. So this is my input. So this is P2 with Q1. So this will be P2 with Q1. Okay. Now, see what is the discharge? See, let it be discharge the same. Let it be Q or M or whatever it may be. It's the same discharge. So the output from here is also same discharge. But here I am getting a higher pressure. Okay. Then from here I will go to the next machine. I'll go to the next machine. So this is my third compressor. So what is the output here? The pressure input is 3, P3 and discharge is Q. So what is the output here? It is 4 discharge. So this is my what I'm going to go to. So here if I want high pressure and same discharge. Whenever I want high pressure and same discharge, I prefer series arrangement of compressor. This is how the multi-staging will work. I am trying to show you as simple as possible. So when I will go for parallel multi-staging, when I want high discharge at same particular exit pressure, and when I go for series arrangement, when I want high pressure and same discharge. So this is how your multi-staging will work. So what is the advantage of this multi-staging? The multi-staging is whenever I want higher pressure, which is more than 10. So then I'll go for this particular thing. Now, so already you know that enthalpy entropy diagram. Okay. So if you know the enthalpy, let us try to draw the enthalpy entropy diagram for a compressor. Then we'll try to derive it. So expression for a pressure ratio, expression for the pressure ratio of a compressor. Okay. So if you want to know the expression for pressure ratio of a compressor, whether it is a axial or a radial one, it remains the same. So let's try to draw the enthalpy HS diagram, or we call it as enthalpy entropy diagram. Okay. So let's try to draw that. This is my H and this is my H. Okay. This is H and S. Then the pressure lines have to go. So they are not parallel, but they are almost diverging. So this is my pressure diagram. So this is P2, this is P1 if it is static, or if you want in terms of dynamic, I can put P01 and P01 and P02. Now, if I go for a single stage compression, this is a single stage compression. So I will start from 0, 1, it's a straight line, isentropic. So it's an isentropic line. I'll go like this. So this is my 0, 1 to 0. So I can call it as 0, 2 dash or 0, 2s. No, there is an actual one. So the actual one is always, it will be curved one to the right hand side. So which will be slightly bigger than your ideal one. So this is my P02. So this is an ideal one, or we call it as isentropic, and this is my actual. So this is for a single stage what I have shown. Now, if we want to derive the expression for the pressure ratio, we have to start with steady flow energy equation. Okay. So let us be the starting point with steady flow energy equation, which you already know the first law of thermodynamics. So the steady flow energy equation, so to obtain the expression, the steady flow energy equation for the steady flow energy equation for the turbo machine or your compressor. So let us write it. So it is Q dot, okay, plus, that is heat transfer, m dot, I will write in terms of enthalpy, that is H1 plus V1 square by 2 plus G into Z1 is equal to m dot into H2 plus V2 square by 2 plus G into Z2 plus I have the work done. Now, what is this H actually? H is equal to U plus CV, which already we know this. Now, if you closely observe this particular thing, I have to ensure that there is no heat loss. Okay, then your turbine or the compressor is in parallel condition, that is in the horizontal position. So that's the assumption. So what I'm going to do actually, so let's assume there is no heat loss, that is equal to 0, and your Z1 is equal to Z2. What is the meaning of it? It's the horizontal position. So the equation gets reduced to m dot into H1 plus V1 square by 2 is equal to m dot into H2 plus V2 square by 2. Okay, then plus your W. Now see here I'm going to put plus or minus W. Why it is actually, if it is a work producing machine like a turbine, this would have been a plus. If it is a work absorbing machine, this will be minus. Okay, depending upon the type of machine what I am trying to look into that. Now, so here see a minus W indicates it is a work absorbing machine like compressor or a fan or whatever it may be. If it is a plus W, it is a work producing machine, which is your turbine. So here we are trying to write an expression for the compressor. So in that case, this has to be negative value. So what I am going to do actually here, this I am going to simplify further. So what is H naught? See, we have seen H naught is your stagnation enthalpy, which is equal to H plus V square by 2. So what I am going to do, I am going to write this as H naught 1 and this as H naught 2. So I can write, so the above expression I can write it as m dot into H naught 1 is equal to m dot into H naught 2 minus W, or I can write, simply simplify the same thing, or W is equal to m dot into H naught 2 minus H naught 1. See, what is small h naught and h naught? They are specific enthalpies. See, your h naught, it indicates specific stagnation enthalpy. Okay. If I multiply this by mass flow rate, it becomes a total enthalpy. So m dot into h naught 2, I can write it as total enthalpy. That is, W is equal to capital H naught 2 minus capital H naught 1. So what is this actually? It is the total enthalpy, total stagnation enthalpy. So now, if you closely observe, we have studied in our thermodynamics. What we have studied? We have studied that your enthalpy is a function of temperature. That is, H is a function of temperature, and if I try to bring in equality constant, it is Cp, so specific heat. Similarly, your U is also a function of temperature. I can write it as U is equal to Cv into T. Why this is actually? Why this is? Because H is a function of temperature and U is a function of my temperature. So now if you try to write this particular thing in terms of temperature, if I call this as expression number 1 or so, okay, if I call this as expression number 2, so the 2 can be written as W is equal to m dot, if I try to open in terms of this particular thing, Cp into T02 minus T01. T02 minus T01. So what is this T02 and T01? See, T02 and T01 are the absolute temperatures. Okay, they are absolute temperatures. Okay, so now if I try to go back and see from your HS diagram, I can write some kind of an efficiency. What is the efficiency here? If I write in terms of enthalpy, there is something called as actual enthalpy drop to the ideal enthalpy drop, if it is a turbine. Or if it's a compressor, actual, see, the ratio of your ideal compression enthalpy, that is the change in enthalpy, to actual your change in enthalpy. So for one turbine, I can write in terms of an efficiency, or for a compressor, I can write in terms of. So here, if I try to write it here for if I call that as a total efficiency or a compressor efficiency, H02 dash minus H01 divided by H02 minus H01 will become an efficiency. So we can write the efficiency for the compressor. So the efficiency for a compressor from the HS diagram, I can write it as either a compressor efficiency or why it is called as total efficiency. I am trying to plot with respect to total values or stagnation values. That's why it's called as total. I can write it as H naught 2 dash minus H naught 1 divided by H naught 2 minus H naught 1. If I try to write the same thing in terms of Cp, I can write it as Cp into T naught 2 dash minus T naught 1 divided by Cp into T naught 2 minus T naught 1. Or Cp simply cancel out. I can write this as the total to total efficiency or compressor efficiency. I can write it as T naught 2 dash minus T naught 1 divided by T naught 2 minus T naught 1. So let me call this as expression number 3 or 4. 3, I think, yeah. So if I call this as 2, I can carry it as 3. So here what I'm going to do, I'll do a simple. So this I call it as 3. This 3 I'm going to write in terms of temperature difference. That is, so I will write T naught 2 minus T naught 1 is equal to T naught 2 dash minus T naught 1 divided by total to total efficiency. That's all. Simply a cross multiplication I did. Okay. Now, if you go and check, see, this is the T naught 2 minus T naught 1, what I have, and I will go and check from the expression T naught 2 minus T naught 1. So, substitute for T naught 2 minus T naught 1 is the work done expression from this expression. If I substitute for it, so substitute for the temperature change from equation 4 in my work done expression. So what will happen to your work done expression? Your W, I can write it as, see, your W is equal to, you have Cp into T naught 2 minus T naught 1. I will write Cp into T naught 2 dash minus T naught 1, okay, divided by your total to total efficiency. Okay, or I can write, see, I can write W by Cp as T naught 2 dash minus T naught 1 divided by total to total efficiency. Okay, whatever the way I want, I can write it. So now W by Cp, see, W by your Cp, see, this particular thing I can write it as W by Cp. Cp is equal to T naught 2 dash minus T naught 1 divided by total to total efficiency. Let me call this as expression number 5. Okay. Now, what is this actually? This is your actual work done. Okay. W by Cp is equal to m dot into T naught 2 minus T naught 1. Okay. Or W by Cp is equal to T naught 2 dash minus T naught 1. I have this particular expression. Now, what I want actually, I want this expression in terms of pressure ratio. Okay. So now, if you go back and see your temperature expression from the adiabatic process, okay, for an isentropic compression from the thermodynamic relationships, for an isentropic compression from the thermodynamic relation. What it is actually, you know, if I try to consider here, see, the only idea is your ideal, what I'm trying to consider. So I have an expression, hope you remember, T2 by T1 is equal to P2 by P1 whole to the power of gamma minus 1 by gamma. Okay, hope you remember this expression was there. So from the isentropic relation, we have this expression, that is T2 by T1 is equal to P2 by P1 whole to the power of gamma minus 1 by gamma. This is the expression what we had in our thermodynamics. Now this is for an stagnation values. I can write for this particular process between the compression process, I can write it as T naught 2. That is, what is it actually? This is an isentropic process. So the higher temperature is T naught 2 dash. So T naught 2 dash by T naught 1, T naught 2 dash by T naught 1 is equal to P naught 2 by P naught 1 whole to the power of gamma minus 1 by gamma. Or I want in terms of pressure. So I can write it as P naught 2 by P naught 1 is equal to T naught 2 dash by T naught 1 to the power of gamma by gamma minus 1. Okay. Now, so this I am calling it as equation number 6. See, I need to substitute 5 in equation 6. Okay. If I want to do that, I need to do little bit of something I need to do mathematically so that I can fit in the equation 5 in equation 6. To do that, what I want to do, I'll take the equation 6, okay, I'll just add, see, T naught 2 dash minus T naught 1 plus T naught 1. So what I'm trying to do, add and subtract, okay, add and subtract T naught 1 in the numerator, T naught 1 in the numerator of equation 6. If I do that, so divided by T naught 1 whole to the power of gamma by gamma minus 1. So now what will happen? If you go and check, see now T naught 2 dash minus T naught 1 from equation 5. So from equation 5, if I want to substitute, what it will be? T naught 2 dash minus T naught 1 is equal to W by Cp into your total to total efficiency. Okay, that is simple little bit of cross multiplication. If I do T naught 2 dash minus T naught 1 is equal to W by Cp into your total to, I can substitute over here. So equation, the pressure ratio equation can be written as P naught 2 by P naught 1 is equal to W by Cp into your total to total efficiency plus T naught 1 whole thing divided by T naught 1 whole to the power of gamma by gamma minus 1. I got this expression. So now further I can simplify this. So further I can simplify. What it is actually? It will be P naught 2 by P naught 1 is equal to W by Cp into total to total efficiency divided by T naught 1 plus T naught 1 by T naught 1, that will become 1. So gamma by gamma minus 1. So few books, what they give actually, they give this expression. That is P naught 2 by P naught 1 is equal to W by Cp into total to total efficiency divided by T naught 1 plus 1, or 1 plus W by Cp. So same expression I can write in R, whatever the way I can write. So this will be P naught 2 by P naught 1, okay, 1 plus W by Cp into total to total efficiency divided by your T naught 1 gamma by gamma minus 1. So both the expressions are fine. I am calling this as expression number 7. So what is your W? So W is the work done. So W is the work done. Suppose substitute for W from the Euler equation. See, this is your expression. We have derived the expression for pressure ratio. We got this expression. Can it be further simplified? Yes. It can be further simplified based on your availability of what we have. Okay. So if I try to look into that particular expression, what we have, so from the Euler equation, let us consider from the Euler equation, that is Euler equation, we have for W, what it is actually, it is for a compressor, it is VW2 into U2 minus VW1 into U1. Okay. Now, for most of the compressor, see, for no whirl condition at the inlet, no whirl condition at inlet, your VW1 is equal to 0. So for this condition, your W will be equal to simply VW2 into U2. So then I substitute for this condition. See, I can substitute for this VW2. In that condition, I can get it. Okay. So substitute for this condition, what I want to get actually, VW2, W over there, my pressure ratio equation will be something like this. P02 by P01 will be equal to W, I will write it as VW2 into U2 divided by Cp into your total to total efficiency divided by T01 plus 1 whole to the power of gamma by gamma minus 1. So this is the expression for your pressure ratio after substituting the value of your W from the Euler equation and trying to get in terms of pressure ratio. Okay. Now, so we have another condition. What is it actually? We call that as radial exit condition. Okay, we have, so this is for no whirl condition. So we have another condition, the radial exit condition. Radial exit condition. What it is? See, if you know that, say for example, people can understand from the exit velocity triangle. See, I have the velocity triangle something like this. So this is my blade. I am trying to draw the exit velocity triangle at the exit, that's the outlet. So this is my your VR going out, okay, VR2, and the fluid is going out something like this. Okay, this is my V2 and your U2. Okay, this is my U2. I have this condition. Now, what will be the condition for a radial exit condition? What is the meaning of it, radial exit condition? So what will happen? Your VW2, what will happen to your VW2? Okay, you have your U2. See, for this condition, if I try to, okay, this is my your VF2 and this is my VW2. Okay. So a condition such that your VW2 and U2 both are same. VW2 is equal to U2. It's radial exit condition. So when my B, you see this beta is there, no, this beta, this is my beta, this is my alpha. So what they have a condition where your beta 2 becomes 90 degrees. So that is called as radial exit condition, your blade exit condition. So for that condition, my velocity beta 2, okay, this is my U2 and this will be my V2 and your VR2 is equal to VF2. This is my alpha 2. So your U2 and VW2 both are same. So this is one of the conditions where we do this as a radial exit condition. That means my beta 2 is equal to, that is the blade angle at exit is 90 degrees. So we call that as a radial exit condition. So condition, my VW2 is equal to U2. Then what will happen to your W? See, we have this W equation from the Euler equation, that is VW2 into U2. So when VW2 is equal to U2, either I can write this will become either VW2 square or I can write U2 square. Either of it I'll do. But preferably, we will write in terms of U2 because it's easy for us to calculate the U2 based on the your 2 pi n by 60 or pi d n by 60 depending upon the diameter. So preferably we write in terms of U2. So for this condition, my equation 7 can be written as, so for this condition, for the radial exit condition, the equation 7 can be written as P naught 2 by P naught 1. I can write it as, so your W I can write it as U2 square, okay, U2 square into your efficient U2 square by Cp, U2 square by Cp into total to total efficiency divided by T naught 1 plus 1 whole to the power of gamma minus 1 by gamma. So if you call this as equation 8, I can call this as equation number 9. Okay. Now, see, you have this particular condition. So one is the inlet whirl is 0, that is VW1 is 0, and I have another condition where your exit condition at the fluid out, that is beta 2, that is blade angle is exact in the radial direction. I may end up with this particular equation. Okay. So we have another condition, what is called as where the energy itself is not utilized properly. Okay, where the energy itself is not utilized properly, and that condition we call it as a slip. Okay, we call it as a slip. Okay, now what is it actually? If there is a slip, your VW2, what we call that VW2 will change. That VW2 will change. You will end up with what is called as a smaller VW2 instead of a bigger VW2. Okay, so whenever I have a smaller VW2, so your whole energy which was supposed to be something like 10 Newton meter, it will be 9.5 Newton meter. Your exit, so what will happen? This will bring down your work factor. To understand this, let us try to, so we have, so this is about expressions. So the expression for the pressure ratio is, these are the expressions. So one is based on the, see, equation 7 is the pressure ratio equation. Then we have two different special conditions. One is a no whirl exit condition, no whirl condition at the inlet, and the second condition is a radial exit condition where beta 2 is equal to 90. Now, when you have this kind of an expression, there is these are the ideal conditions. There is an actual condition is also there. To understand this actual condition, we need to study what is called as slip and slip factor. Slip and slip factor. What is this actually? Now let's try to draw the exit velocity triangle. Okay. So this is my maybe the tip actually, and I'm trying to draw the velocity triangle, something like this. So this is the blade is there. Okay. Suppose this is my VR2. So I have my V2 going here, which is going out, and I have the your U2. This is my U2. Okay, this is my U2, and I have my VF2 like this. This is my VF2, and this is my VW2. Those are the components, and this is my beta 2. This is my alpha 2. This is how the velocity triangle looks like. Now, there is a condition where this VW2 will become smaller. What will happen? See, when this condition, say when this V2 is pulled a little bit smaller, that means my exit velocity is smaller. See, this is the velocity. When my exit velocity itself is smaller, so I'll redraw this particular velocity triangle again with the condition that V2, see, when this particular V2 becomes smaller, I may end up with a condition something like this. So you may end up with a condition where, so suppose this is my V2, and what will happen to your VW2? So VW2, this will become smaller, and what will happen to your alpha 2? Alpha 2 becomes bigger. So you have a new what is alpha 2 dash, your VW2 dash. Okay, so this factor, we call it as delta VW, that is called as slip. The reduction in the, so what is slip actually? Slip is the reduction between your actual whirl velocity to your, see, it's the ideal whirl velocity to actual whirl velocity. So we call that as delta VW2. So there is a reduction. What will happen? See, the work done. See, the work was supposed to be this much. See, VW2 into U2. So your new work done will be VW2 dash into U2. U2 also will get reduced. So U2 dash. So because of this, my work done will get reduced. The slip will reduce your work actually. So there is a difference in your velocities. There is a difference in your tangential velocities. We call it as a tangential velocity. That is called as your whirl velocities. So let me write that. So because of the slip, because of the slip factor or the slip, there is a difference in your tangential velocities. Difference in tangential velocities. Tangential velocities at the of the ideal and actual. See, tangential velocities of the ideal and actual at the exit. At the exit. What is it actually? I will call that as a 2 or whatever it may be. So this is called as slip. Then there is something called as slip factor. That means actual whirl velocity to your ideal whirl velocity. If I take the ratio of it, I will end up with what is called as slip factor. So this is your slip. So we have another thing what is called as slip factor. So which is the ratio of, so usually we call it as sigma, the slip factor. It is the ratio of actual whirl velocity or tangential velocity at exit of the compressor to ideal whirl velocity at the exit of the compressor. So what it is actually? It is VW2 dash by VW2. If I take the ratio of it, whatever I am going to get, I call that as slip factor. Okay, that is denoted by the sigma. So that is denoted by sigma. So we have another term which is called as slip coefficient. Slip coefficient. What it is actually, it is called as phi. It is the ratio of slip actually. It is the ratio of slip to your ideal whirl velocity. So what is your slip actually? We call that as VW2 minus VW2 dash divided by VW2 or delta VW2 divided by VW2. So these are some of the factors which are required to define what's happening. Now, if I consider the slip, what will happen to your pressure ratio equation and all? Your pressure ratio equation will reduce. Okay, your pressure ratio equation will reduce. So what will happen? The work is also will get reduced. If I try to input this particular VW2 dash and all those things over there, what will happen? If slip is considered, okay, if slip is considered, then what will happen to your equation 7? If you come back to this equation 7, you see here what I will substitute for W. So what is W? So W is nothing but VW2 into U2. So instead of VW2, I will put VW2 dash into U2. Okay, VW2 dash into U2, whatever it may be. If I try to put that, what will happen? Or your VW2 dash, I can write it as sigma into VW2. because sigma is equal to VW2 dash by VW2. Then the equation will get reduced. So I am trying to bring in a factor, what is called as a slip factor, which clearly tells, let's say if the slip factor is around 0.9, so it is 90% efficient, or 0.95, it is 95% efficient. I am trying to bring in the actual things what is happening over there rather than ideal one. So I can write P02 dash, see I can write P02 dash by, sorry, P02 by P01 is equal to VW2 dash into U2, okay, divided by Cp into your total to total efficiency or compressor efficiency divided by P01 plus 1 whole to the power of gamma by gamma minus 1. Now what is your sigma? Sigma is equal to VW2 dash by VW2, or I can write VW2 dash is equal to sigma into VW2. So if I substitute for this, therefore my P02 by P01, I can write it as sigma into VW2 into U2 divided by Cp into total to total efficiency divided by T01 plus 1 whole to the power of gamma by gamma minus 1. So this I am calling it as equation number maybe 8 or 9. So this equation 9. So this is the condition for your pressure ratio under slip condition. So instead of stagnation values, if there is a static condition, okay, for static conditions, what will happen? Instead of P02 by P01, I can write it as P2 by P1 is equal to sigma into VW2 into U2 divided by Cp into, instead of total to total efficiency, this will be a simple static to static efficiency, because that is based on your static values, plus 1 whole to the power of gamma by gamma minus 1. So this I am calling it as equation number 10. Okay. It's the same equation for a radial exit condition, if I write. For a radial exit condition, where beta 2 is equal to 90 degrees, because what is there in that condition? Your VW2 is equal to U2. I can write the same expression as P02 by P01 is equal to sigma into U2 square divided by Cp into your total to total efficiency divided by T01 plus 1 whole to the power of gamma minus 1. Or if I want in terms of static, I can write it as P2 by P1 is equal to sigma into U2 square by Cp into static to static efficiency divided by T1 plus 1 whole to the power of gamma by gamma minus 1. I can call this as equation number 11. So these are some of the equations. Okay. So these are some of the equations which clearly tell us that the pressure ratio can be written in